Here's another theorem that states the obvious. If two angles are both supplementary and congruent, then they are right angles. Well, we can show this algebraically because the definition of supplementary angles is two angles whose measures have a sum of 180. We can write the equation m plus m is 180 because if they're congruent, they both have the same measure, so we only need the one variable. And then, of course, that means that 2m is 180, and we divide both sides by 2, and we get that 1m is 90. And, of course, the definition of a right angle is an angle who has a measure of 90 degrees. We can also write a paragraph proof for this to set it up. We would just need to say that angle 1 is supplementary to angle 2, and that angle 1 is congruent to angle 2, and our job is to prove that angle 1 and angle 2 are right angles. This particular proof does not need an accompanying diagram. Here's our paragraph. The measures of angles 1 and 2 have a sum of 180 degrees by the definition of supplementary angles. Each angle then must have a measure of 90 degrees because congruent angles have equal measures. They both must be right angles by the definition of right angles. And in this example, we're going to look at one of the most common situations where we concern ourselves with supplementary angles that are congruent, and that is when they are adjacent. And so in this particular proof, we don't need to state that they're supplementary because we have the accompanying diagram. And in the accompanying diagram, because of the way the diagram is written, we get to assume that they're a linear pair. So here's our paragraph proof. Angles 1 and 2 are supplementary because they form a linear pair. The measures of angle 1 and 2 have a sum of 180 degrees by the definition of supplementary angles. Each angle then must have a measure of 90 degrees because congruent angles have equal measures, and they both must be right angles by the definition of right angles. And here's a corollary to Theorem 23. If two angles that form a linear pair are congruent, then they are right angles. So now we'll work through a couple of proofs that will use either our new theorem or the corollary to our new theorem. And here's a proof. We're given a diagram of a triangle that appears to be isosceles, and it is because it's given that AB is congruent to AC. So we'll mark it as shown. We're also given that BD is congruent to CD, and we'll mark that as shown. And of course, by definition of a midpoint, that tells us that D is a midpoint. And while we're at it, we could note that because of what we're given, we now know that AD is a median of this triangle. But that's not what we're trying to prove. We're trying to prove that AD is also an altitude to the triangle. Well, we might want to mark that AD is congruent to itself, or perhaps we might want to mark that angle B is congruent to angle C, because if sides, then angles. But now you can see that if our goal is to prove that triangle ABD is congruent to ACD, we have more than enough to prove that. So let's start our statements and reasons. Well, we'll start by stating one of the givens, and then it makes sense to state the other given. And now you see that we've proved a pair of sides, so we're on our way to proving a pair of triangles congruent. We have a choice. We could use side angle side by using the angles that we know, or we can go side, 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 and that's the one we'll pick because AD is congruent to itself. I hope you know the reason, the reflexive property. So now I hope you can write the two triangles that are congruent. There they are. And of course, the reason, side, side, side. And as you probably know by now, often when we prove a pair of triangles congruent, the next thing we're going to show is that a pair of their corresponding parts is congruent. And in this case, it's angle ADB congruent to ADC. And of course, the reason for that is corresponding parts of congruent triangles are congruent. And then we're going to state that they're supplementary. And we can see that from the diagram because they form a linear pair. We're also going to state that those two angles are right angles, and that's from the theorem, that congruent and supplementary angles are right angles. And then we get to state that AD is an altitude by the definition of an altitude, and this proof is complete. And now we'll look at a couple of definitions. A segment bisector is a line, ray, or segment that intersects a segment so as to divide the segment into two congruent segments. More specific than just a segment bisector is a perpendicular bisector, and that's a line, ray, or segment that bisects and is perpendicular to a segment. Well, let's do one more proof. And in this proof, we have a diagram, and we have a couple of givens. And we're going to take our two givens and mark them YZ congruent to WZ and XY congruent to XW. And some of you may already know that that makes the four-sided figure YZWX something called a kite, because the top two sides, which are adjacent, are congruent, and the bottom two sides, which are adjacent, are congruent. We'll study kites more in later lessons. What we're trying to prove here is that segment ZX is the perpendicular bisector of segment YW. Well, as we do in most proofs, the first thing we state is one of the givens, and there it is. And you can see that it looks like we're going to try to prove a pair of triangles congruent. So we have a pair of sides. Then we'll state the other given, and we have a second side. And now we have to decide which pair of triangles we're going to prove congruent, but it looks like it's going to be ZYX and ZWX. And in order to do that, we'll state that XZ is congruent to itself, and I hope you know the reason for that. Of course, the reflexive property. So here's our two triangles that we've just proved by, I hope you know, side, side, side. And from that, we're going to pick out a pair of corresponding parts. And notice I've got a red A. We've done this in an earlier lesson. This is a detour proof. Now we're going to prove a second pair of triangles congruent. We have YZU congruent to WZU by corresponding parts. And then we have ZU congruent to itself, reflexive property used again. And we have a side and an angle. And we're going to use another side, and it's a pair that we've already done, so we mark it in red from step 1, the given. So now we have a side, angle, side for another pair of triangles. The triangles are YZU and WZU. And there it is, side, angle, side. And from that, we're going to get another pair of corresponding parts, but this pair is from the new pair of triangles, CPCTC. And we can see that those two are supplementary because if you look at those two angles, they of course form a linear pair. And since we've already proved them congruent, and we know that they're a linear pair from our earlier theorem, we know that they're both right angles, because congruent and supplementary angles are right angles. Stating that UY is congruent to UW goes back to line 7, the two triangles we proved congruent because of corresponding parts. So now we've proven a second pair of corresponding parts from the two triangles that were proven in line 7. And you'll notice we're running out of room, but now we've proved enough to state that ZX is a perpendicular bisector of YW by the definition of perpendicular bisector. In this lesson, we looked at a theorem. If two angles are both supplementary and congruent, then they are right angles. We also looked at the corollary to that theorem. If two angles that form a linear pair are congruent, then they are right angles. And a pair of definitions. A line, ray, or segment that intersects the segment so as to divide the segment into two congruent segments is a bisector of the segment. And more specifically, perpendicular bisector. A line, ray, or segment that bisects and is perpendicular to a segment is the perpendicular bisector of that segment.